Hello, everyone. Today, we're diving into an exciting project where we're building a machine learning model for seizure detection using EEG images. We'll walk through the process of setting up TensorFlow, training a convolutional neural network, and deploying it using Flask. Feel free to ask questions or provide feedback as we work through this. If you're new here, make sure to check out the Biomedical website for more tools and resources. Let's get started. Here's an overview of the key packages and why they are important for your project. 1. TensorFlow. Purpose. TensorFlow is an open-source machine learning framework used for building and deploying machine learning models. It supports deep learning and neural networks, making it essential for tasks like image recognition, natural language processing, and more. Usage in your project. TensorFlow is likely being used to build and train models for analyzing biomedical data, such as detecting patterns in EEG data related to seizures. 2. Protobuf. Protocol buffers. Purpose. Protobuf is a method developed by Google for serializing structured data, useful in applications that need to store and exchange data efficiently. Usage in your project. TensorFlow uses Protobuf to define and serialize data structures, such as the neural network models you are working with. Keras. Purpose. TF-Keras is TensorFlow's implementation of the Keras API, a high-level neural networks API that simplifies building and training models. Usage in your project. It provides a user-friendly interface for creating neural networks, which is crucial for developing and experimenting with different model architectures in your project. 4. TensorFlow Decision Forests. Purpose. This package provides tools for working with decision forests, a type of machine learning model that includes decision trees, random forests, and gradient-boosted trees. Usage in your project. It might be used to compare or complement the deep learning models with decision forest models, especially in tasks like classification or regression, where decision trees can be very effective. HANA 5. TensorFlow.io GCS file system. Purpose. This package allows TensorFlow to interact with Google Cloud Storage. It's part of TensorFlow's input-output I/O ecosystem, supporting various file systems. Usage in your project. If your data or models are stored in Google Cloud Storage, this package facilitates seamless access and interaction within your TensorFlow workflows. 6. TensorFlow.js. Purpose. TensorFlow.js is a library to run machine learning models in the browser or on Node.js using JavaScript. Usage in your project. This might be used to deploy your trained models directly to the browser for real-time inference, which could be useful in web-based biomedical applications where users interact with the model through a web interface. General overview of your project. You are working on a biomedical data processing application, likely involving the detection of patterns in EEG data, such as identifying seizure activity. To build this application, you are using TensorFlow to develop and train deep learning models. These models are likely being designed to analyze large datasets of EEG images and signals. By using these tools, you aim to create a robust system capable of processing biomedical data, which could be deployed for real-time analysis or integrated into a web-based tool for broader accessibility. In your current setup, you're working on a complex project involving machine learning and data processing, likely related to biomedical applications, given your past work with ECG and EEG data. Here's a general overview of the key packages you've been dealing with. TensorFlow, a core machine learning framework that's widely used for developing and training deep learning models. It provides a flexible and comprehensive set of tools, libraries, and community resources that enable researchers and developers to build machine learning models with ease. Keras, an API within TensorFlow that simplifies the process of building neural networks. Keras is designed to be user-friendly, modular, and extendable, making it easier to experiment with different architectures and approaches. Protobuf, a serialization tool used to encode structured data efficiently, crucial for communication between different components of a machine learning pipeline. TensorFlow uses Protobuf to save models, configure them, and manage communication between different parts of a system. MediaPipe, a framework specialized in processing multimodal data streams, such as video and audio. It is particularly useful in real-time applications like gesture recognition, face detection, and other tasks requiring quick processing of continuous data streams. In summary, these packages collectively enable you to develop sophisticated machine learning models, particularly those that involve processing and analyzing real-time biomedical data. They provide the necessary infrastructure for building, training, and deploying models, while also handling the complexities of data serialization and real-time processing. This code represents a complete pipeline for building a convolutional neural network, CNN, to classify EEG images as either seizure or non-seizure events. The broader goal of this project is to leverage deep learning techniques to assist in the automated detection of seizures, which is particularly important in the field of neuroscience and medical diagnostics. The project begins by loading EEG images stored in two directories, one for seizure events and another for non-seizure events. The images are grayscale and resized to a standard size of 128 by 128 pixels. The load images from folder function reads these images, converts them to arrays, and assigns a label to each, 1 for seizures, 0 for non-seizures. The images and labels are combined into a single dataset. Next, the images are normalized, meaning their pixel values are scaled to be between 0 and 1, which helps the model converge faster during training. The data is also reshaped to fit the input requirements of the CNN. Labels are one-hot encoded, transforming them into a format suitable for binary classification. The data is then split into training and validation sets. The training set is used to teach the model, while the validation set is used to evaluate its performance on unseen data. The CNN is built using several layers. Convolutional layers, Conv2D, to detect patterns in the images. Max pooling layers, Max pooling 2D, to reduce the dimensionality of the data, while retaining important features. A flatten layer to convert the 2D output into 1D, dense layers to make predictions based on the features extracted by the convolutional layers. A dropout layer is included to prevent overfitting by randomly setting some outputs to 0 during training. The model is compiled with the atom optimizer and binary cross-entropy loss, which are standard for binary classification tasks. Data augmentation is applied to the training data using image data generator, which randomly transforms images to make the model more robust to variations in the data. The model is trained over 10 epochs, and its performance is evaluated using the validation set. Finally, the trained model is saved for future use, and its validation accuracy is printed. In summary, this project uses a CNN to classify EEG images, aiming to assist in the detection of seizures by processing and analyzing brainwave data through image-based techniques. The code covers the entire process from loading and pre-processing the data to training, evaluating, and saving the model. The image you provided appears to be a screenshot of a web application focused on an EEG seizure detection project. The application is designed to help users explore and understand EEG, electroencephalogram data, particularly in the context of detecting seizures. In the field of neuroscience, EEG is used to monitor electrical activity in the brain, which can be critical in diagnosing and managing conditions like epilepsy. The web application seems to allow users to visualize spectrograms, which are graphical representations of the frequency spectrum of EEG signals over time. These spectrograms are used to differentiate between seizure and non-seizure EEG segments. The left spectrogram represents non-seizure data, while the right represents seizure data. The application provides an interactive interface where users can select datasets and analyze the visual patterns in these spectrograms. The slider below each spectrogram might be used to navigate through the EEG data or to adjust parameters such as the frequency range displayed. The science behind this involves transforming raw EEG signals into a frequency domain using techniques like the Fourier transform, allowing for the identification of patterns that are characteristic of seizure activity. This visualization aids in the machine learning process, where algorithms can be trained to automatically detect seizures based on these patterns, which is valuable for clinical applications in monitoring and managing epilepsy. Overall, the project integrates data science, machine learning, and neuroscience to create a tool that not only educates, but potentially assists in real-world medical diagnostics. Package version control can be challenging due to the interdependencies among various software libraries. Each package may rely on specific versions of other packages to function correctly. As software evolves, new versions of packages introduce changes, fixes, or new features that might break compatibility with other packages or with older versions of the same package. This creates a complex web of dependencies where upgrading one package can inadvertently cause others to fail or behave unpredictably. Another challenge is that different projects may have conflicting version requirements. For example, one project might require a newer version of a package to access the latest features, while another project might depend on an older version for stability or compatibility reasons. This situation is exacerbated when using a shared environment where different projects rely on the same environment settings, leading to potential conflicts. Moreover, the rapid pace of software development means that new versions of packages are released frequently, sometimes with major changes. Developers must stay vigilant to keep up with these changes while ensuring that their applications continue to work as expected. This balancing act requires careful testing and validation, which can be time-consuming and error-prone, particularly when dealing with large and complex projects. Lastly, package managers, while helpful, sometimes struggle to resolve these dependency conflicts automatically. They may choose versions that satisfy one part of the dependency tree while inadvertently breaking another. As a result, developers often need to manually specify package versions and test extensively to ensure compatibility, making version control a delicate and ongoing task in software development. Upgrading everything to the latest version sounds ideal, but it often introduces compatibility challenges. Not all packages update at the same pace, and some may depend on specific versions of other packages that are not yet compatible with the latest versions. In your case, upgrading NumPy to the latest version, 2.10, caused issues because SciPy and scikit-learn still rely on a NumPy version from the 1.x series. The ecosystem of scientific computing libraries in Python is complex, with many interdependencies. Libraries like NumPy, SciPy, and TensorFlow are foundational, meaning many other packages depend on them. When one of these libraries updates, it often requires the maintainers of dependent packages to adjust their code to ensure compatibility. If the maintainers have not yet done so, users who upgrade to the latest versions might encounter errors or broken functionality. This is why version control and dependency management are critical. Sometimes, the most stable environment is achieved not by having the latest versions, but by using versions that are known to work well together. By downgrading, you're aligning all your packages to versions that are tested and known to be compatible, ensuring that your code runs smoothly without errors. Your current script has several issues that need addressing to ensure that it runs correctly and produces meaningful results. Here's what's wrong and how these issues can be addressed. 1. Model definition duplication. The script defines the model twice, which is unnecessary and can lead to confusion. You first define the model using an input layer, and later you define it again with an input shape in the first comp2d layer. This redundancy should be eliminated, and you should stick to one approach. 2. Improper input shape handling. You correctly use input in the first model definition, but then redefine the model with the input shape argument in the first conv2d layer. The more modern approach recommended by Keras is to use the input layer to specify the input shape, which you did correctly the first time. 3. Incorrect use of steps per epoch and validation steps. The training might be ending prematurely because the steps per epoch and validation steps are not calculated properly. These should be based on the exact size of your dataset and possibly adjusted to ensure the generator can yield enough batches per epoch. 4. Warnings and deprecations. The script contains warnings related to the use of older practices, such as saving the model in the HDF5 format. The script should be updated to use the recommended .keras format for saving models. 5. Error handling and data verification. The script checks if directories exist but doesn't have robust handling if the images aren't found, leading to possible empty datasets being fed into the model. This needs better error handling to ensure the model doesn't try to train on empty data, which could be causing some of the zero accuracy issues. 6. Possible out-of-range error during training. There's an indication that the data generator might be running out of data. Out of range, end of sequence. This suggests that your generator is not properly set up to handle the number of steps per epoch, which could lead to training stopping prematurely. Summary of what needs to be fixed. 1. Remove the duplicate model definition and use the input layer approach consistently. 2. Correctly calculate and handle steps per epoch and validation steps based on the dataset size. 3. Update the model saving method to the .keras format. 4. Improve error handling for loading images to ensure there's valid data for training. 5. Address the out-of-range issue by ensuring your generator can yield enough data for each epoch. Once these issues are addressed, the script should run more reliably, allowing for proper training and evaluation of the model. Let's proceed with regenerating the corrected version of the code. Let's break down the output messages and the overall training process of your model. 1. Initial system logs. The first set of messages indicate that TensorFlow is initializing and checking the system's configuration. Specifically, it mentions that 1DNN custom operations are on, which means TensorFlow is using a library optimized for CPU performance. However, it also indicates that CUDA drivers for the GPU are not found, so GPU acceleration will not be used. This is why TensorFlow is running solely on the CPU. The warnings about libraries like QFT, QDNN, and QBLAS failing to register are related to the absence of a CUDA-enabled GPU on your system, which is expected since the script doesn't require GPU computation. 2. Model training logs. The output shows that the training process starts with epoch 1 out of 10. For each epoch, you see the accuracy and loss for both the training, accuracy and loss, and validation datasets, val accuracy and val loss. The user warning mentions that your PyDataset class should call a specific initialization method. While this warning does not stop the training, it suggests a potential inefficiency in how data is being processed, particularly in how the dataset is being prepared for training. Another recurring message is the warning about the input running out of data, prompting an early stop to the training. This is crucial because it suggests that the number of steps per epoch may be larger than the available data batches, causing TensorFlow to run out of data before completing all steps in each epoch. This might be happening because the number of batches available does not match the steps per epoch parameter. Ideally, this parameter should reflect the actual number of batches available, so the model doesn't expect more data than exists. 3. End of sequence warnings. Multiple times, you see a warning stating, local rendezvous is aborting with status out of range, end of sequence. This is a direct consequence of the model running out of data during training, leading to TensorFlow terminating the epoch early. The data generators might not have enough batches to satisfy the steps per epoch parameter, which results in this end of sequence message. Model performance. Throughout the training process, you see fluctuations in the training accuracy, but they stay within a certain range, starting around 50% and stabilizing without significant improvement. This suggests that the model might be struggling to learn effectively from the data. The final validation accuracy at the end of the training is around 51%, which is just above random guessing, 50%. This indicates that the model hasn't learned to distinguish between classes, seizure versus non-seizure, effectively. The val loss and val accuracy outputs are crucial for assessing how well your model is generalizing to unseen data. The fact that the validation accuracy is low and barely changes across epochs suggests that the model might be underfitting, meaning it's not complex enough or hasn't been trained enough to capture patterns in the data. 5. Model saving and final accuracy. Finally, the model is saved, and the last step is the evaluation on the validation dataset. The validation accuracy is reported as 51.04%, which confirms the model's performance is close to random chance. In summary, the key issues seem to be with how the data is being fed into the model during training, leading to end-of-sequence errors, and the overall performance of the model being low, indicating it is struggling to learn from the data. This could be due to various factors like the complexity of the model, the amount and quality of the data, or how the data is being augmented and fed into the model. Given the output and the analysis, here are the next steps you should consider. 1. Adjust the data generator. Modify the steps per epoch and validation steps parameters in your model.fit call to match the actual number of batches available in your training and validation datasets. This will prevent the end-of-sequence errors. You can calculate these values by dividing the total number of images in your training and validation datasets by the batch size. 2. Increase model complexity. Consider increasing the complexity of your model by adding more layers or increasing the number of filters in your convolutional layers. This can help the model learn more complex patterns in the data. 3. Hyperparameter tuning. Experiment with different hyperparameters, such as learning rate, batch size, and number of epochs. You might also try different optimizers, e.g. RMSprop, SGD, to see if they improve the model's performance. 4. Data augmentation. Review your data augmentation strategies. While you are already applying rotation, width, height shift, and horizontal flip, consider whether these transformations are appropriate for your dataset. You could also explore other augmentation techniques like zoom, shear, or brightness adjustments. 5. Address potential data issues. Ensure that your dataset is balanced and of good quality. If there is a significant class imbalance, consider techniques like oversampling, undersampling, or using class weights in your loss function to address this. 6. Validation and testing. Implement a separate test set evaluation after training to measure the true generalization of your model. Ensure that your validation set is representative and not overlapping with your training set. 7. Analyze model performance. After training, analyze the confusion matrix to understand where your model is making mistakes. This can help you refine your model further or pre-process the data differently. Once you make these adjustments, rerun the training process and monitor the outputs closely for improvements in both training and validation performance. Given the directory structure you provided, it looks like you have a well-organized dataset for training, validation, and testing your seizure detection model. The dataset is divided into subdirectories labeled Train, Val, and Test, each containing images organized by their respective categories: non-seizure and seizure. Next steps. 1. Verify data consistency. Ensure that all images are correctly labeled and in the appropriate directories: Train, Val, Test. This will help avoid mislabeling and ensure that the model learns accurately. 2. Calculate steps per epoch. Given the number of images in each directory, calculate the steps per epoch and validation steps. This can be done by dividing the number of images in the training and validation sets by the batch size. Example, if you have 600 images in the training set and a batch size of 32, steps per epoch equals 600/32, 19, 3. Adjust the training script. Update the training script to reflect the correct steps per epoch and validation steps values. This will prevent the end-of-sequence errors observed earlier. 4. Check for data augmentation. Review your data augmentation techniques. Ensure they are appropriate for your dataset and that they are applied consistently during training to improve model generalization. 5. Model evaluation. After training the model, evaluate its performance on the test set to measure its generalization capability. This will give you an unbiased assessment of the model's performance. 6. Analyze results. Analyze the validation accuracy and loss. If the accuracy is low or the loss is high, consider adjusting the model architecture, hyperparameters, or training strategy. 7. Save and document the model. Once you are satisfied with the model's performance, save the final model and document the entire process. This includes noting any changes made, such as data preprocessing steps, model architecture adjustments, and training strategies used. These steps will help ensure that your model is properly trained and evaluated, leading to better performance and more reliable predictions. To adjust the training script without using code, focus on the following key areas. 1. Adjusting steps per epoch and validation steps. Based on the number of images in your training and validation datasets, calculate the appropriate values for steps per epoch and validation steps. These values help the model process all batches in each epoch without prematurely running out of data. Ensure these values align with your batch size to avoid errors during training. 2. Enhancing data augmentation. Review the data augmentation techniques you're applying. Consider if they are enhancing the model's ability to generalize from your training data to unseen data. Adjust rotation, width, and height shifts and flips based on the characteristics of your dataset to introduce variability that the model can learn from. 3. Model evaluation during training. Implement techniques to visualize the model's performance as it trains. This can include plotting the loss and accuracy for both the training and validation sets after each epoch. This allows you to monitor the model's learning process and identify issues such as overfitting or underfitting early on. 4. Real-time visualization. Utilize visualization tools to track the model's progress during training. This could be done using libraries that create live plots of metrics like loss and accuracy. Visualizing these metrics in real time will provide immediate feedback on how well the model is learning and allow you to make necessary adjustments on the fly. 5. Analyzing results. Post-training. After training, thoroughly analyze the final model's accuracy and loss on the validation set. Compare these with the training metrics to assess how well the model has generalized to unseen data. Investigate any significant differences between training and validation performance, which could indicate overfitting or underfitting. 6. Saving and documenting the model. Once satisfied with the model's performance, save the trained model securely. Additionally, document the entire training process, including the final model architecture, hyperparameters used, data pre-processing steps, and any challenges encountered during training. This documentation will be invaluable for future reference or for others who may work on the project. By following these prompts, you can effectively modify your training script to improve model performance and ensure a robust and well-documented machine learning pipeline. To update your current code and improve its functionality based on the previous discussion, follow these steps. 1. Steps per epoch and validation steps adjustment. Ensure that the steps per epoch and validation steps parameters are calculated based on the size of your training and validation datasets. This helps ensure that each epoch processes all batches of data correctly. The updated code includes these adjustments. 2. Real-time visualization of training progress. To visualize the model's performance as it trains, consider incorporating callbacks that log the accuracy and loss metrics after each epoch. You could also integrate live plotting tools, like Matplotlib or TensorBoard, to visualize these metrics in real time. This approach allows you to monitor overfitting or underfitting trends during the training process. 3. Saving the model. The model is saved in the recommended Keras format, .keras, instead of the older HDF5 format. This ensures compatibility with newer versions of TensorFlow and Keras, which favor this format. 4. Detailed model evaluation. After training, the model is evaluated on the validation set, and the results are printed out. This evaluation includes both loss and accuracy, giving you insight into the model's performance. 5. Documentation and analysis of results. Beyond coding, it's crucial to document the training process, including the final model architecture, hyperparameters, and any observed issues during training. This documentation will help you or others replicate or further develop the model in the future. By incorporating these changes, your training script will be more robust, providing real-time feedback on model performance and saving the model in a forward-compatible format. This setup also lays the groundwork for better model evaluation and documentation practices.